I believe it's true to say that in operating the power plant, the operators do not pay too much attention to the generator. Whether the generator is driven by a steam turbine, gas turbine, or even a water turbine, it is an extremely reliable piece of equipment which continues to produce electricity while demanding very little attention from the operator. It seems that most of our activities are focused upon the turbine end, while the generator looks after itself. But we should never allow ourselves to forget that certain operating features of the generator are extremely important. And for this reason, it is necessary to brush up on this subject from time to time. In this videotape, we're going to take a look at typical construction features of the power generator and also discuss important factors related to operation and control. The purpose of the generator is to receive the rotating mechanical energy which is produced in the turbine and convert this into usable electricity at a specified terminal voltage. All modern power generators produce three-phase power. We'll be discussing this in greater detail later in this tape, but at this point, we're focusing our attention on the physical arrangement of the components which make up the generator. The electricity is actually produced in the stator winding. This is the stationary winding which is supported by the stator frame. The stator winding consists of insulated copper conductors which are embedded in the slots of the stator core. The slots run end to end. The so-called iron core is made up of laminations of special steel. Each individual lamination or plate is coated on one side with an insulating material. The objective of this is to reduce the flow of induced eddy currents through the core. This in turn reduces the heat loss of the iron core and thus keeps the temperature down. The laminations are tightly packed together and secured within the stator frame. Once the stator bars are fitted into the core slots, they are joined at the ends to form continuous coils or windings. These end connections are referred to as end turns. The conductors are securely held in the slots by wedges of insulating material. This is extremely important, as the windings themselves are subject to quite heavy mechanical forces during operation. The windings may try to twist during heavy power surges or electrical faults on the power system. Similar distortion of the windings may occur if the generator is badly synchronized, that is, synchronized when out of phase with the system. One of the few problems that can occur on generators is the loosening of the windings, with resultant vibration and increased temperature rise and perhaps damage to insulation. The stator conductors are connected together in various series and parallel arrangements so as to produce the rated terminal voltage, say 13.8 kilovolts, and rated current output, say 6,000 amps. The stator windings are connected to the terminals, usually at the bottom of the generator. Outgoing conductors will be connected at these terminals in order to carry power to a bus or power transformer, and perhaps an auxiliary transformer. VTs, voltage transformers, are also located close to the terminals to provide input to the generator voltage control system. Current transformers are usually located close to the terminal bushings. These CTs measure the value of current and transfer this information to the control and protection system. In some generators, surge capacitors and lightning arresters are located at the terminals so as to protect the generator windings. Heat is produced within the generator in three ways. Current flowing in the stator winding produces heat called I²R copper loss. Friction between the spinning rotor and the air, or hydrogen, in the generator produces heat called windage loss. Stray induced current in the iron core produces heat called iron loss. If the internal temperature rise is too high, it will damage the insulation and put the generator out of service. For this reason, distinct limits are placed on permissible temperature rise. In order to monitor this, temperature detectors are embedded in the stator windings at the anticipated hotspots, and these readings are continuously recorded and alarmed when necessary. Forced cooling is employed to keep the temperature rise as low as possible, either by hydrogen cooling or air cooling. We'll be talking more about this in the next segment, but first, let's move our attention to constructional features of the rotor. The function of the rotor is to provide a rotating magnetic field. The rotor is coupled to the turbine and thereby receives all of the mechanical energy. This mechanical energy is then transferred across the rotating magnetic field to the stator windings, where it is converted into electrical energy. The rotor is supported at each end by journal bearings. These must be very accurately aligned so as to maintain the same precise clearance between rotor and stator all the way along the length of the core. A forced lubrication system is required for the bearings. Pressurized lube oil may be provided from the turbine lube oil system, or in some cases a separate generator lube oil pumping system is installed. On many units, the top of each journal bearing is vented through a vapor extractor. This creates a slight vacuum inside the bearing and so prevents any oil vapor from accumulating inside the generator housing. So the rotor provides the rotation, but where does the magnetic field come from? Well, I suppose this could be provided by a permanent magnet, but this would provide no means of control, and probably the field would not be strong enough. In actual fact, the magnetic field is created by a rotor winding. Insulated solid copper conductors are embedded in rotor slots, and they are located in such a manner as to form a huge coil which turns with the rotor. DC current is passed through the rotor winding in order to produce a magnetic field with a north and south pole. Of course, the next question is, where does the DC come from? Well, there are two possible sources depending upon the design of the machine. A common arrangement is to provide DC from a rectifier located in a nearby panel. This is known as static excitation. The DC is applied to the rotor winding through brushes running on collector rings. An alternative source of DC excitation is from a shaft-mounted exciter. In this case, connection leads are run inside the shaft, and therefore no brushes or collector rings are required. The magnitude of DC current and voltage applied to the rotor windings is quite low, say 600 amps at 250 volts. Typically, the generator will be housed in a compartment like this. Access is provided to allow maintenance and inspection of the collector rings or brushless exciter. This particular generator is air-cooled, and the air is in turn cooled using water carried in these pipes. Generally, in modern installations, the generator rotor is directly coupled to the turbine shaft. However, some turbines are designed to run at much higher speed, say 5,000 to 7,000 RPM. In this case, the generator is coupled through a gear drive in order to drive the generator rotor at the correct speed, that is 3,600 RPM for a 60 hertz generator. But what is it that determines the speed requirement? Well, we'll talk about this later. For now, let's take a break. Please switch off the tape and review this material in your workbook. The cooling system is a vital component of generator operation. As we mentioned in the last segment, the amount of power which a generator can supply is limited by the temperature rise of the windings. And therefore, the more efficient the cooling system, the more load can be placed on the generator. For most gas turbine installations, air cooling is employed, usually open cycle. The air is actually circulated through the generator by fans, which are fitted at each end of the rotor. As the rotor spins, the fans provide the moving force to circulate the cooling air through the rotor and stator core. Cooling ducts are often built into the rotor and stator core to allow passage of cooling air. This diagram shows a typical arrangement. Air is drawn in from atmosphere and passed through filters to remove any particles of dust or other contaminants. The air is then drawn down through silencers into the fan impeller at each end. The air is then exhausted radially from each fan under pressure, and this is directed to follow the desired cooling path, eventually exhausting to atmosphere via the gear drive in this particular unit. In some units, silencers are also fitted to the air exhaust. Usually a separate cooling system is provided for the exciter or collector rings. In this particular arrangement, a small fan impeller is fitted in the collector air inlet, adjacent to the collector rings. Air is pulled in through a filter to circulate through the terminal connections and collector rings. As we can see, this system is self-contained and requires no attention from the operator other than to ensure that the filters are clean and allowing sufficient air to pass. The pressure drop across the filter will indicate when it needs to be replaced. On standby or peaking units, this task can easily be performed when the unit is out of service. However, on continuously operated base load units, automatic continuous filter cleaning is usually installed. The provision of clean air is absolutely essential, as the ingress of dust and other particulate matter may block cooling passages and may even cause grounding and consequent damage to the insulation. Where the generator is located in a hostile environment, say very dirty conditions, the closed cycle air cooling system is usually employed. In this case, the same air is continuously circulated through the unit, and the air itself is cooled as it passes through a water-cooled heat exchanger. Because of the additional pressure drop across the heat exchanger, it may be necessary in some generators to add a circulating air fan. Make-up air to compensate for any leakage is admitted into the suction of the circulating fan. Filters are provided on the make-up air inlet from atmosphere. In other designs, the shaft-driven fans are made larger so as to avoid the need for a separate air circulation fan. With this arrangement, make-up air is drawn in by the fan suction through the generator housing. As we have already mentioned, air cooling systems are used on most gas turbine generators. However, when the unit size increases above, say, 100 megawatts, then hydrogen cooling is normally employed. There are several advantages to using hydrogen as a cooling medium instead of air. Hydrogen is less dense than air, and consequently the windage loss, that is, friction loss due to rotation of the rotor, is considerably reduced. Hydrogen has a much greater capacity to absorb heat than air, therefore it is a better cooling medium. These two advantages mean that the generator can be made smaller than an equivalent air-cooled generator of the same capacity. Therefore, on the larger size generators, it is more economical to install a hydrogen-cooled system, even though this entails a much more complicated cooling system. The generator casing is built as a sealed unit, with hydrogen inside the casing being maintained at a pressure of about 30 psig, say 3 bar. Not all units operate at the same hydrogen pressure, so make sure that you know the operating conditions for your particular unit. Actually, the higher the hydrogen pressure, the greater the cooling effect, and consequently, the MVA output of the generator can be increased. The hydrogen is circulated within the generator by shaft-mounted fans, similar to the arrangement for air-cooled generators. The heat picked up by the hydrogen is extracted by passing the gas through water-cooled heat exchangers. Some adjustment of cooling water flow through the hydrogen coolers may be necessary to maintain optimum temperature of the hydrogen gas. This is normally performed automatically. As the hydrogen is maintained at a positive pressure inside the casing, there is no possibility at all of air entering from outside. This is a distinct advantage, as it ensures that the generator internals operate under ideal, clean conditions. On the other hand, the presence of hydrogen under pressure does have a slight negative factor, that is, the loss of hydrogen by leakage. Leakage could conceivably occur through joints in the casing, particularly around the terminal bushings, but the most likely area is through the shaft seals. We'll talk more about this in a moment. Generally speaking, the loss of hydrogen is very small, but this still needs to be compensated. Make-up hydrogen is added through an automatic pressure regulator, which is set to maintain the desired internal hydrogen pressure. The hydrogen manifold may be fed from hydrogen bottles or perhaps from a hydrogen tank installed in the plant. In order to prevent hydrogen leakage around the shaft, hydrogen seals are fitted beside the bearings at each end of the generator. A common type of hydrogen seal consists of spring-loaded labyrinth segments which lightly hug the shaft under spring tension. The segments are lubricated by seal oil, which is maintained at a pressure of about 5 psi above the pressure of hydrogen inside the generator. Consequently, it is impossible for hydrogen to leak out past the seal. Seal oil leak-off is then drained back to the seal oil pumping system. Any hydrogen that may have been absorbed by the oil is drawn off by a vacuum pump, which forms part of the seal oil unit. This small amount of hydrogen leakage is then discharged to atmosphere. The seal oil pumping system is a very important part of the generator operation. It must be placed in operation before the generator is charged with hydrogen and then maintained in service at all times. A decrease in seal oil pressure will be alarmed, and the operator must take immediate action to rectify the situation. Usually a standby seal oil pump is installed, and in addition to this, a DC emergency pump is provided in case of loss of AC auxiliary power. Are there any dangers involved in handling hydrogen? Well, the answer is yes and no. For example, a small leakage of hydrogen into atmosphere presents no danger at all, as the hydrogen is completely diluted by the large quantity of air surrounding it. Also, at the other end of the spectrum, pure hydrogen cannot ignite and so presents no danger. However, certain mixtures of hydrogen and air do present an explosive mixture. The danger area for an explosive mixture is within the range of 20 to 70% hydrogen in air. For this reason, it is extremely important to maintain the purity of hydrogen inside the generator. Ideally, the hydrogen purity should be above 97%. Purity is continuously monitored and indicated and alarmed if the level falls below the set point. But you may well ask, if the hydrogen comes from hydrogen bottles, how can it be other than pure? Why is it not 100%? Well, the fact is each bottle of hydrogen does contain perhaps a minute quantity of air, and this eventually accumulates inside the generator. I'm sure that those of you who already operate hydrogen-cooled generators know that with time, the purity does begin to fall. In order to raise the level of hydrogen purity, it is necessary to purge the generator. That is, to vent gas from the generator to atmosphere and replace this with new gas directly from the hydrogen bottles. In this manner, we are exhausting gas which contains, say, 96% hydrogen and introducing gas of, say, 99.8% purity in its place. This will improve the average purity in the generator. So all of this ensures that we keep the gas mixture well above the upper explosive limit. But what about the mid-range? Well, this potential problem occurs when the generator is shut down for maintenance and we need to open it up for inspection. How can we discharge the hydrogen without it coming into contact with air in the explosive range? You will remember that we talked about this in an earlier tape. The problem is resolved by eliminating the possibility of hydrogen and air coming into contact with each other inside the generator. First, the generator is purged of hydrogen by filling it with CO2 under pressure. CO2 is a completely inert gas that is non-flammable and non-explosive. The CO2 gas is admitted under pressure through a manifold at the bottom of the generator casing. This gas is much heavier than hydrogen. As it fills the generator casing from the bottom upwards, it slowly rises and pushes the hydrogen out of the top manifold. The correct valve arrangement must be selected by the operator so as to allow this top manifold to discharge to atmosphere instead of receiving hydrogen from the bottles. The vent is usually located at high altitude, and there is no danger, as the hydrogen is immediately diluted by surrounding atmosphere. During this process, the gas inside the generator casing is monitored, and when this indicates close to 100% CO2, the purging is complete. The generator can then be opened up to atmosphere and the CO2 allowed to escape while air takes its place. Sometimes an external blower may be used for this purpose. The total time required for purging may take several hours. When the generator is to be readied for service, then the reverse action takes place. Initially, the generator will be full of air. CO2 will then be admitted at the bottom manifold to push air out from the top. When all air has been expelled, hydrogen will then be admitted from the top manifold, so forcing CO2 out of the bottom. This is quite a tedious process and requires much care and attention from the operator. Make sure that you learn the specific procedures for your particular generator. Of course, for a short overnight shutdown of the machine where generator maintenance is not required, the generator remains charged with hydrogen with the seal oil system in operation. To prevent excessive leakage from the seals, it is important that the shaft rotate continuously on the unit turning gear. It is quite apparent that operation of the hydrogen cooling system is much more complicated than generator cooling by air. However, I am sure that those of you who have worked in steam power plants are quite familiar with these activities. In this tape, we've dealt with the fundamentals of the different cooling systems. Make sure that you thoroughly learn the details of the specific cooling system which is installed on your generator. At this point, it's time for a break. Please switch off the tape now and review this material in your workbook. So far, we have been looking at constructional details of typical power generators. But how does the generator actually produce electricity? Now, I'm sure you'll all remember going through this subject in study of basic electricity, perhaps several years ago. But do you still remember, say, the difference between single-phase and three-phase power, or the significance of increasing or decreasing excitation, and what is meant by reactive power? We feel that it will be worth our while at this point to review generation fundamentals so as to lay the foundation for our discussion on generator control. This simple AC generator consists of a coil or rotor rotating in a magnetic field. The magnet has north and south poles and its magnetic flux passes through the rotor. By convention, the lines of force or flux leave from the North Pole, pass through the rotor, and then return to the South Pole. So the lines of force at the South Pole are set up in the opposite direction to those at the North Pole. In this diagram, as we start rotation of the coil, one side passes close to the North Pole and one side close to the South Pole. The coil sides cut the magnetic lines of force, and in doing so create a voltage in the coil. This is the well-known principle of electromagnetic induction. When a conductor cuts a magnetic field, a voltage is induced in that conductor. At 0 degrees, the coil is not cutting any magnetic flux at all, and therefore the induced voltage is 0. The value of induced voltage is maximum when the coil is in the 90-degree position, because here we have the maximum rate of cutting magnetic lines of force. The direction of induced voltage in the blue conductor is opposite to the voltage in the red conductor. The voltmeter therefore receives the sum of the two voltages. As the rotor moved from 0 degrees to 90 degrees, the voltage has increased like this. And then, as the rotor moves from 90 to 180 degrees, it decreases like this. As the coil continues rotation past this 180-degree position, the conductors are cutting flux from a different pole. The red conductor is now in front of the North Pole, and the blue conductor is in front of the South Pole. So the voltage generated is now in the opposite, that is, negative direction. So we can see that one revolution of the coil produces one cycle of alternating voltage. It is alternating because one half of the cycle is in the positive direction, and the other half is negative. We have been moving the coil with the magnet in a fixed location. This is basically what's done in the brushless exciter, which provides the excitation voltage or rotor voltage for some AC generators. This will be discussed in segment E of this tape. However, this is not a practical arrangement for large AC generators, as huge slip rings would be required to take the large AC generator output current from the rotor. We could, however, rotate the magnet and hold the coil fixed to produce an AC voltage. This is what is done in most AC generators. One of the principal tasks in designing an AC generator or alternator is to construct a combination of magnetic fields and coil configurations that produce a true sine wave at the generator terminals. If we connect this circuit through a resistance and an ammeter, we find that the current follows the same pattern as the voltage. The positive and negative half cycles mean that the current is flowing in one direction for half the cycle, and then in the opposite direction for the other half cycle. As the magnet continues to rotate, it produces further cycles of voltage and current like this. These curves are known as sine waves, and values can be calculated from trigonometric tables. This, then, is how AC voltage and current are generated. You can see that for each revolution of the magnet we have one cycle. So if the rotor is spinning at, say, 60 revolutions per second, then we will generate 60 cycles per second. You recognize this, of course, as frequency, usually stated as 60 hertz. 60 revolutions per second is equal to 3,600 revolutions per minute. And I am sure we are all familiar with that number. By contrast, a two-pole machine on a 50 hertz system, as used in Europe, needs to run at 3,000 RPM. On some generators, the rotor is built with 4 poles instead of 2. That is, 2 north poles and 2 south, like this. Now, each single revolution of the rotor will generate 2 complete voltage cycles. So at what speed will the generator need to run in order to produce a frequency of 60 hertz? This can easily be calculated from the standard expression that says frequency equals P, that is the number of poles, over 2 times N, that is revolutions per minute, over 60. In this case, 4 over 2 times N over 60 equals 60 hertz. Therefore, N equals 1800. The 4-pole machine must run at 1800 RPM to produce 60 hertz. You can see that the required speed of the generator depends upon the frequency and the number of poles on the rotor. In practice, instead of a rotating permanent magnet, the magnetic field is provided by an electromagnet. The rotor winding actually forms a large coil, and this is fed with DC to create the north and south poles. The DC field current is known as excitation. Increasing the value of DC current increases the strength of the magnetic field up to certain limits, and vice versa. Now let's look at various ways of connecting stator windings. In this basic arrangement, the two ends of one stator winding are brought to the generator terminals and then connected to feed a single-phase load. In order to generate a second voltage, we can use an additional stator winding, which is placed at an angle of 120 degrees from the first winding. An AC voltage will also be generated in this winding, and it too can be connected to feed a single-phase load. But note its generation cycle, that is, minimum and maximum, occur at a different time period. In fact, the cycle of phase 2 is 120 degrees behind phase 1. That is a time lag of 5.5 milliseconds on a 60 hertz system. In a similar fashion, we can utilize a third stator winding, which is placed yet another 120 degrees, that is 240 degrees from phase 1. This too can be connected to feed an individual single-phase load. And once again, its generation cycle is 240 degrees out of phase with phase number 1. So what we have in effect here are 3 independent windings supplying 3 independent loads, but each using a common iron core and rotating magnetic field. Almost 3 generators in one. But there is a further advantage. By connecting one end of each stator winding to a common neutral point, we can provide one single return conductor for the circulation of current from all 3 phases. As the currents in these 3 phases are out of phase, the positive and negative flows in the neutral occur at different times and therefore have a tendency to cancel each other out. In fact, if the load on each phase is identical, that is a balanced load, we find that the return current in the neutral completely cancels out to 0. Therefore, we can eliminate the neutral. We now have the conventional 3-phase system as you know it. The 3 outgoing terminals from the generator are connected by 3 lines to the 3-phase load, that is, the bus or power transformer. This in turn feeds the 3-phase power system. Most of the heavy loads on the system are actually 3-phase balanced loads. For example, electric motors. Moreover, single-phase loads, such as residential loads, are connected to the distribution system in such a way as to provide an approximate balance. The common connection of the stator winding, usually known as the neutral point, is often connected to ground. However, there are several other ways of connecting generator windings, but this is certainly beyond the scope of this program. If you'd like to know more about this subject, please refer to our other video programs. So let us now turn our attention to synchronizing. When the generator is switched into the power system, it is not sufficient to just close the circuit breaker. Certain definite conditions must be set up before the generator can be synchronized to the system. The first thing is that the generator must be running at its rated speed. This is done by adjusting the governor set point. Second, the generator terminal voltage must be adjusted to equal that of the bus to which it is being synchronized. This is done by adjusting the excitation. As the strength of the magnetic field is increased or decreased, so will the terminal voltage rise or fall. The third, very important factor is that the incoming generator voltage must be in phase with the bus voltage. What do we mean by this? Well, look at this example showing one phase only. Here is the sine wave representing the bus voltage, and here, superimposed, is the incoming generator voltage. You can see that the generator is over 90 degrees out of phase. If we closed the breaker in this condition, the generator would attempt to pull itself into phase. This could twist the windings and the stator core and create considerable damage. Of course, the great surge of power would be detected and the breaker immediately opened by protection devices. In order to provide the correct conditions for synchronization, we need to very gently adjust the speed of the incoming generator so as to bring it into phase with the bus. At the moment that the two are in phase, the breaker should be closed, and the unit will then lock into synchronism with the power system. On most modern units, this synchronization is performed automatically. However, you may find the need to do this manually on certain occasions. For this purpose, a synchroscope is provided. This is connected to either side of the breaker and, in fact, indicates the difference in phase between the two sides. For example, this condition shows that the generator is 90 degrees out of phase with the bus. As the pointer is stationary, it also indicates that the speed, that is, the frequency of both the system and the incoming generator, are identical. More often than not, you will see the pointer slowly rotating like this, indicating a slight variation in speed. In this case shown, the incoming generator is running slightly faster. If the rotation is slow enough, you can manually close the circuit breaker just before the pointer reaches the midnight position. The machine will then lock itself in synchronism and start providing load. In order to further increase power output, it is necessary to add more torque to the unit. This is done by increasing the fuel input to the gas turbine. But can we not also increase power output by increasing excitation? The answer is a definite no. Increasing the excitation will only increase voltage to a certain extent and will also increase the reactive power output of the generator. We'll be talking about this later. Let's first take a break and then we'll come back and continue our discussion with a look at generator control. For now, please switch off the tape and thoroughly review this material in your workbook. As you would expect, the generator is well equipped with indications, alarms, and trips to provide protection. Alarms are triggered to warn of such conditions as high bearing temperature, abnormal lube oil conditions, high stator winding temperatures, high temperature of inlet cooling air or hydrogen, low seal oil pressure differential on the hydrogen system, low hydrogen purity, high rotor winding temperature, electrical protection relays to trip the unit in case of a generator electrical fault. Essentially, control of the generator is concerned with three items: control of megawatt output by adjusting fuel input, control of megavar output by adjustment of excitation, control of terminal voltage also by adjustment of excitation. Let's look at megawatt output first. This is known as active power. This is the power which actually does useful work for the consumer. For example, you burn kilowatt hours in your light bulbs and electric heaters. You pay for kilowatt hours to run your appliances. The megawatt or kilowatt is the component of power which does the work. As we know, the demand for megawatts varies throughout the day as consumers switch on or off their load devices. As we cannot store electrical energy, at least in large quantities, the combined power output of all of the generators which are connected to the system must exactly equal the total power demand at every instant of the day. The total power demand consists of the consumer's demand plus power system losses, which may be as high as 4 or 5%. If at any time the power demand is greater than power production, then the frequency will fall. It is the load dispatcher's job to keep system generation and load balanced, and he must do this while paying attention to the economic loading of units, which means the most economical generating units should be fully loaded first. At the same time, he has to allow for limitations in the transmission system, say due to line outages. So the load dispatcher's job is quite a handful, just as much as the gas turbine operator's. However, he is assisted by computer programming and by automatic devices such as the turbine governor and the dispatcher's automatic generation control system. We mention all this as background so that you may well appreciate the dispatcher's urgent appeal to you sometimes for rapid increase or decrease of unit output. We know that in order to change the generator megawatt output, we must change the energy input, that is the fuel input to the gas turbine. This may be performed in several ways. Manually by the operator in accordance with predetermined loading instructions, or on request from the dispatcher. Automatically by the turbine governor, which responds to changes in turbine speed, which is of course related to system frequency. Automatically by the dispatcher's AGC if the unit is used for regulation, that is, to assist in frequency control. Gas turbines have considerable advantage in assisting frequency control because of their capacity for relatively fast load changes. Most of the machines on the system, that is, steam turbines, gas turbines, and hydro turbines, will operate on governor control. If there is a sudden increase in system load, all of the machines immediately slow down, and this is immediately detected by the governors. Governor response opens up the fuel inlet or steam inlet valves, and so increases the unit outputs in order to meet the increased load demand. This action takes about 10 seconds to stabilize. Now remember, all of the units which are connected to the power system are running at precisely the same synchronous speed. This is obvious because they are synchronized together and the frequency is precisely the same at all points of the system. So how is it then that one unit may operate at, say, 100% capacity and another at 50%? Does this mean that the unit with the greatest load is running faster? Well, beware of this trick question. Of course, it cannot run faster because, as we just said, the units are all synchronized together. So how does it then put out more load? Well, the answer is in the load angle or power angle. This is the relative angle between the induced voltage due to the rotor and the terminal voltage which is dependent upon the power system. This diagrammatic representation shows the situation at zero load. The rotor and the stator voltage are exactly in phase. If we wish to increase the load output from the unit, we add more fuel to the prime mover. This initially accelerates the rotor so that it moves ahead in phase. There is now a power angle or load angle created between the rotor and the stator voltage. This in turn causes power to flow from the generator into the system. To further increase power output, we add more fuel and so further increase the load angle, which in turn increases the power output. In each case, the rotor settles down to its new condition and continues to run at that load angle. At maximum load, the load angle will probably be about 60 degrees. So now you can see that if we have, say, 3 units in parallel on a common bus, the unit which is generating at 100% capacity will have a load angle of about 60 degrees. The unit at 50% output will have a load angle of about 30 degrees, and the unit at zero load has a load angle of 0 degrees. Okay, so much for power output of the generator. Let's now take a break, and then we'll come back and talk about voltage control, excitation, and megavar output. For now, please switch off the tape and review this material in your workbook. Control of the generator output voltage is affected by adjusting the magnitude of excitation current. We already know that increasing excitation results in an increase in the strength of the rotating magnetic field. This in turn brings about an increase in the voltage, which is induced into the stator conductors. Let's take a closer look at the excitation system to see how this control is carried out. First, we'll look at a simplified arrangement of the static excitation system. DC current from the rectifier is supplied to the rotor winding through the collector rings on the shaft. The incoming AC to the rectifier is supplied from a dedicated transformer. The primary side of this transformer is fed from an auxiliary bus, or in some cases, the generator bus itself. The sine wave for the incoming three-phase AC voltage, which is applied to the rectifier, will look like this. After rectification, the DC output can be represented by this curve, and this may be further smoothed to look like this. The level of DC voltage can be adjusted by controlling the firing of the thyristor type rectifier. The firing circuit itself is controlled by the field voltage regulator. This regulator has 2 inputs, manual and auto. The manual control disconnects the automatic function and allows the operator to directly control excitation. However, when the generator is in operation, the field voltage regulator is usually controlled from the auto position, that is, from the AC voltage controller. This controller monitors the generator bus output voltage through VTs and automatically adjusts excitation so as to maintain the set point voltage. The operator can adjust this set point and thus exercise control while the excitation system is operating in auto. All of these components of the static excitation system are normally located in a so-called excitation panel close to the generator. Of course, the auto and manual control inputs will also be located on the operator's panel. Another type of excitation system often used with gas turbines is known as the brushless exciter. The exciter is actually a small AC generator which is built onto the end of the generator shaft instead of collector rings. In this exciter, a stationary magnetic field is provided from the DC winding, which is wound on the stator. The rotor winding produces AC voltage, and this is fed directly into diode-type rectifiers, which are built into the shaft. So we have, in effect, a rotating rectifier. The DC output from the rectifier is connected directly to the main rotor winding through leads which pass inside the shaft. There is no need for collector rings or brushes. An exception is shown in your workbook where the generator is used as a startup motor. Control of the DC excitation current is effected by adjusting the strength of the exciter magnetic field. And this is done by controlling the DC current flow through the field winding. This DC field current is supplied from a rectifier which is located in a nearby cabinet. Of course, this rectifier is much smaller than the static rectifier that we previously studied because it is supplying field current only to the rotating exciter. But control is effected in the same manner. That is, by adjusting the firing of the thyristors. And this in turn is governed by the field voltage regulator. The arrangement at this point is similar to the static exciter. When in auto, the field voltage regulator receives its command signal from the AC voltage controller, which in turn monitors the output voltage of the generator. The operator can adjust the AC set point as required. When starting up the unit, the field voltage regulator may be set to manual, and in this case the operator will control the regulator directly. So what is the effect of adjusting excitation? Well, obviously, one effect is to adjust the output voltage of the generator. For example, by increasing the excitation current, the generator terminal voltage will increase. But that's not all that happens. As terminal voltage is increased, the generator will produce and transfer more megavars into the power system. On most units, the megavar output of the generator is indicated right alongside the megawatt output. The term megavars stands for megavolt amperes reactive. It is actually the unit for reactive power. But what is this reactive power? Well, it is a fact of life that all electromechanical devices, such as transformers, motors, electromagnets, etc., all of these require megavars in order to set up and maintain their magnetic field. For example, let's look at an electric motor. The shaft on the motor rotates to drive a machine and produce useful work, let's say 100 horsepower. The motor will need to draw about 75 kilowatts in order to produce this power output. But in addition to this, the motor will need to draw about 30 kilovars in order to set up the magnetic field which is needed for the motor to function. So on our power system, we have a demand not only for megawatts, but also for megavars. And both of these power components must be supplied by the generators. Fortunately, the provision of megavars does not require any increase in energy input to the turbines. The fact is, reactive power does not absorb any energy at all. The reactive power actually oscillates twice per cycle between the magnetic field of the generators and that of the consumer's equipment. The average power consumed is zero. So why are we concerned about this reactive power? Well, the problem is that even though increased energy input is not required, increased current still flows through the generator windings and through the power system. The result of this is that we could easily overheat the generator windings if we had a high megawatt output plus a high megavar output. Distinct limitations are placed upon the combined total output of megawatts and megavars. Megawatts and megavars act with a different phase relationship to voltage. Active power is in phase, while reactive power acts 90 degrees out of phase. The combination of megawatts and megavars is known as MVA, that is megavolt amperes. You will remember that in a DC circuit, if we multiply volts times amps, we get power, watts. However, in an AC circuit, volts times amps, VA, gives us apparent power, as it is a combination of vars and watts. The ratio of true power, that is active power, megawatts, to apparent power, megavolt amps, is known as power factor. This curve shows us the limitation of MVA due to current in the stator. For example, at this megavar loading, we can only produce this amount of megawatts to stay within the machine's capability. Clearly, in order to keep within the MVA rating, we must reduce megawatt output if we wish to produce a large output of VARs on the generator. However, there are other limits to observe in generator operation. As we know, in order to increase the megavar output of the generator, we must increase excitation. The increase in current flow increases the heating of the rotor winding. This curve shows the limitation due to rotor heating. You can see that we can operate this generator at 180 megawatts and 0 megavars, but if we needed to produce, say, 100 megavars, then we would have to reduce the megawatt output to 140 megawatts in order to keep within the established limits. We also run into trouble if we reduce excitation too much. In this case, as the voltage falls, VARs will flow into the generator from the power system. This is shown on this curve as negative VARs. The problem is, if the rotor current is reduced too much, then the magnetic field may become so weak that the generator will lose stability and fall out of synchronism with the other units on the system. In order to prevent this, a minimum excitation limit is established by this additional curve here. This combination of limits provides the generator capability curve that you should be familiar with. For each specific generator, this curve is normally displayed in the control room. Make sure that you always operate the generator within these limits, whether you are absorbing or supplying megavars and megawatts. Okay, now that we've got you interested in this subject, I have to point out that any further discussion is really outside the scope of this program on gas turbines. If you would really like to know more about electrical system operation, please refer to other of our video programs. Most power companies already have our video programs on power system operation and power system protection and others. At this time, please switch off the videotape and thoroughly review this material in your workbook.